Hello, today we're going to be talking about mass moments of inertia, and we're going to be calculating those via the second moment integral. So to start out, the reason we want to talk about this mass moment of inertia, and this mass moment of inertia is usually abbreviated I. So what it is, it's the second polar mass moment of inertia, or moment integral of a volume. So why is this important? Well, in mechanics, engineering mechanics, this helps us relate the moments applied to a body and the angular acceleration of a body, which is going to be very important in something like dynamics. All right, so the rotational version where we see this relationship is if I've got some moment, that's going to be equal to the mass moment of inertia times the angular acceleration I see in that body. So this is the rotational version of F equals ma. The rotational version of a force is basically a moment. I, or the mass moment of inertia, is the basically rotational version of the mass, the resistance to acceleration, and alpha is the angular acceleration of our body. So this mirrors the kind of more common version of the formula F equals ma. All right, so where we derive this comes from F equals ma. So if we imagine, to start, say we've got a point mass, so some point mass out here, it's got a mass m, and we've got it on the end of a stick that is d some distance long. All right, so say I wanted to kind of rotate this stick, I'm holding it down here, I exert some moment, so some twisting force there, and I observe some angular acceleration. So how would I relate this moment and this acceleration? Well, I'm going to start with F equals ma. And so this stick, if I kind of twist it on this end, the stick is going to exert an upwards force over here, and the mass is going to have some acceleration in that upward direction to match the force. So F equals mass times acceleration. And so I've got F and A out here. All right, so if I want to relate the force I see out here in the moment, well, a moment is a force times a distance, and so a moment over a distance is going to be equal to the force, and so I can substitute in this m over d in for my force, and if I want to relate that linear acceleration I observe out here to the angular acceleration of kind of my piece as it moves around, I can use the following relationship. So the linear acceleration is equal to the angular acceleration times this distance. And so if I substitute in that alpha times d, and I kind of rearrange all that equation, I wind up with the moment is equal to md squared times alpha. So that md squared term is the basis for our mass moment of inertia. All right, so if I take this one step further, so say I've got a bunch of masses, they're all connected back to some central point with their own kind of respective sticks. So if I have some moment, I apply it at that connection point, I observe some angular acceleration. To find the overall relationship between m and alpha, I just take the kind of sum of all of these pieces. So mass 1 times distance 1, mass 2 times distance 2, mass 3 times distance 3, and so on. If I sum all those together, I find some term that directly relates the moment and the angular acceleration. And we go one step further. So for some rigid body, I'm going to imagine this as some kind of infinite collection of very, very small masses. And so each one of those, I imagine they're connected back to the central axis that I'm rotating this thing about via a massless stick. And so the massless stick is an imaginary concept, but what it does is each little bit of mass is held in place and it kind of rotates with the rest of the body because all of this other stuff around it is keeping it from kind of moving independently. And so the massless stick is just everything else kind of holding that little piece in place. And so to sum up an infinite number of very small things, we use calculus. So if I integrate this d squared dm term, So that's kind of the d squared and mass terms over the entire mass. That's going to relate my moment and my angular acceleration. So that is the basis of my mass moment of inertia. That's our moment integral. All right, so starting from the basics, this is our equation. We're integrating over the mass, dm times d squared. And in this equation, we're moving out from some axis. And the distance here represents that distance from the axis for any little bit of mass. So it could be the x-axis, or it could be x-axis, y-axis, whatever axis we're rotating about. This I term is going to depend on our selection of that axis. And generally in mechanics, we're going to have kind of one of two axes. It's either going to be some fixed axis in a rotation, so imagine something like the hinges on a door. Those hinges are fixed and everything rotates about that point. Or we're going to look at some axis moving through the center of mass. So if we have no fixed axis, if the whole thing is moving through space, we do all of these calculations about the center of mass. All right, so next, if the body has a uniform density, aka if it's made of kind of one single material, I've got a steel block, I've got a plastic block, whatever, then we can kind of rewrite the mass as the density times the volume. If density is constant, we can bring it outside the integral. And so I equals the integral of the mass, d squared dm, or if I've got a constant density, I is equal to density times the volume integral of this d squared dv term. So it's additionally important to realize that the distance in our equation will depend on the axis. I talked about this earlier. And so usually we've got some sort of subscript to keep track of this. So Ixx would be the mass moment of inertia about the x-axis. It's going to be density times d squared dv. So moment integral about, or moment of inertia about the x-axis, and these d squared terms are going to be distances from that x-axis. I'm going to have separate Iy and Iz values, and each of those, the distance terms are going to change depending on that term there. All right, so if we go fully into this, we have our kind of overall moment integral equation. So the mass moment inertia about in this case I chose the z-axis for this cone. It's going to be the density of the material. Times, I'm taking the integral from some lowest value of r to some maximum value of r. So as the distance increases from, well, in this cone it would be 0 is the minimum, out to some, this is the farthest point from that central axis here. So r min to r max, and I've got this dv term, and this is where a lot of your work is going to go, is figuring out the rate of change of volume as I move out from this central axis. So something like this cone, if you start thinking about r equals 0 and move out, and as you move out, you've got kind of a cylinder that's expanding. And so the circumference and the diameter of the cylinder is increasing as we increase r. But something like this cone, we start with a very tall, kind of skinny cylinder. And as we move out, not only does the diameter increase, but also the height is decreasing. So it's following this piece down. And so that equation is describing the cylindrical area, so it's the sides of the cylinder here, within the shape at any given value of r. And so it'd be basically circumference times height, and height decreases over time, circumference increases. And we need to multiply that by the rate at which r is changing. And so the rate at which r is changing is just dr. We're going to leave that in there, and that's why we're integrating from r min to r max. We get that dr term. So whatever that equation is for this outside area of my cylinder, I multiply that equation by r squared to find my overall equation, and I integrate that using this from r min to r max. So once I have that, I'm going to kind of just brute force my way through the calculus, force my way through the integral, and wind up with a formula that's going to give us our mass moment of inertia. If I have definite radius, height, etc. I'll get an actual number. Otherwise, you might end up with just a formula. And those formulas you can actually look up. The mass moment of inertia tables, we've got some of those terms. Another important thing to note here is often in those tables you're going to see like mass times some distance or height squared. And the reason you see mass when you don't see it here is they kind of work backwards and get the mass by, at the end of this integration, you're going to end up with some long formula. You've got this density out here. If you can kind of split that formula into two parts, one part being the equation for the volume itself, and you multiply the volume of your shape times the density, that simply reduces to mass, and what's ever left over from the equation you get from this part is going to be the rest of your moment integral equation. So with that, that's all I have for mass moment integrals via integration. Thank you for watching, and I hope to see you again.